Hi students, welcome to the session on important aspects of HC and dipole antenna. Right, so before going through this video, please refer my video on HC and dipole antenna. Then only you will understand the concepts I am going to explain now. Right, in HC and dipole antenna, we derived H pi value. This is H pi value, right? And we know that for radiation, 1 by R is dominant, 1 by R squared is electric field, so that is negligible. So in radiation field, I neglected 1 by R squared. Simply, I kept remaining thing only. So it is I naught j beta L beta dl by 4 pi R e power minus j beta R. So it is for radiation field, H pi is equal to this one, right? H has only phi component, that is rotational magnetic field. Phi is a rotation, right? 0 to 360 degree we know. So like magnetic field rotate around a current carrying conductor, it is rotating in the free space also. That's what it indicates, right? Similarly, we found two fields in the HC and dipole antenna, ER and E theta for electric field, two components of electric field. E phi is 0, right? So E phi is 0. As usual, E phi must be 0 because phi is a rotational component, electric field will not rotate. So E phi must be 0. And ER, E theta, you see, out of these two, 1 by R is radiation component. Others are 1 by R squared is induction, 1 by R cube is dipole. So electric field. So here you see ER doesn't have radiation component, so we can neglect for radiation. Neglect ER for radiation. Only this E theta has radiation component 1 by R, so others are neglected. So what I did is simply eta j I beta dl divided by 4 pi R sin theta e power minus j beta R, right? So for radiation we have only one component of electric field, that is what E theta component only. That's what given here. So magnitude of E theta component is, if you take a magnitude of a complex number j, so j will move away, remaining thing will be as it is. Magnitude of E power j is 1. So that's why eta I naught beta dl divided by 4 pi R sin theta. H phi is, that we know, H, you see here we have H. So take a magnitude, so j will be move away, e power minus j beta magnitude is 1. So remaining thing I naught beta dl 4 pi R sin theta. Otherwise you can see here E is equal to eta H. So this is what our H. You see, that will be there. Okay, so we know E and H value. We know another thing about this is we are using spherical coordinate system. So R theta phi R component. So these are all perpendicular to each other. So from here you see electric field is along theta component, E is along theta direction, H is along phi direction. And we know already when we derived this equation, R, the wave will propagate in R direction. So the wave power flow in the R direction. So you see electric field is perpendicular to magnetic field, which is perpendicular to power flow. That is wave propagation. So even though we use spherical coordinates, the wave is EM wave is spherical, but it is transverse electromagnetic wave. EM wave is spherical, but still it is TEM, transverse electromagnetic field, because all are perpendicular to each other. E is perpendicular to H because E is in theta direction, H is in pi. Right? We know in the spherical coordinate system, R theta phi are perpendicular in nature. So Maxwell's equation is proved, and its experiment is also proved, right? Then, so all are perpendicular to in nature. Then another thing is, we know HC and dipole generates three fields. What are those fields? E field, H field, and radiation field. You see why? You remember here 1 by R is radiation field, this is magnetic field or induction, this and all we know, this is electric field. So similarly for H5 also, it is producing radiation and induction field. So HCN dipole antenna produces all the field, but at far away distance, radiation field is dominant. Radiation field is dominant. Okay, that is the important point we must remember about HCN dipole antenna. The fifth point is, another thing is, we know E theta divided by H phi. If you divide E theta by H phi, what you get is eta value. That is what? 377 ohm. You divide E theta and H phi, we will get eta. Already I told them. So this is E theta divide H phi. So this factor will be cancelling. So what we get is eta. That we know already, right? It is this parameter value and all we know already from our electromagnetic wave discussions, right? So this is very, very important. And the sixth point is, you see, E theta and H phi are varying with respect to theta. Here you see, let us take other factors are constant, right? So you see eta is a constant, current flowing through will be constant, length constant, the radiation field location is constant, everything is constant. So E as a function of theta, Hy is also a function of theta. So E and H are varying as a function of theta. So both electric field and magnetic field are varying as a function of theta. So what is the theta? Sin theta. So E is directly proportional to sin theta. H is directly proportional to sin theta. Others are constant. Proportionality constant we can consider. So if theta is equal to 0, fields are 0. Because sin 0, 0. If theta is equal to pi by t, fields are maximum. Because sin pi by 2 is maximum. Right? So this is very, very important. So other parameters are considered to be a constant one. So what we are going to do, we draw the radiation pattern of HCN dipole antenna as a function of theta only. So E is directly proportional to sin theta. That proportionality constant is that one. I simply write K, sin theta. Okay. So instead of K, we have to substitute eta in a dl, right? Beta dl by 4 pi r. That's not required. Just we call it as a K. So you see how the radiation pattern of HCN dipole antenna will be there. Yeah. Okay. This is what theta is equal to pi by 2. Let us consider theta 0. Fine. And theta is equal to pi. Why? Because I kept my antenna like this. Yes or no? In the diagram I have kept antenna like this. That's why this is 0 degree, this is pi degree. So we know the radiation will be maximum along, fields will be maximum along pi by 2, not and 0 at pi 0. Yes or no? Fields are 0 at 0, maximum at pi by 2. So what is the thing is, the radiation pattern will be looking like this. For HCN dipole antenna, here you see at pi by 2, E is maximum. Right here you see 0 along the direction. So along the antenna axis, this is very, very important conclusion. Along the antenna axis, radiation is 0 for HCN dipole antenna. Right? And radiation is maximum radiation is maximum when in perpendicular direction. In perpendicular direction. This is very, very important. This concept we will use it in the what you call antenna array also. Suppose if antenna is kept, for example, this concept is used in the antenna array, so we have to remember if antenna is kept horizontally. So this is antenna axis, so it is 0, it is pi by 2. Sorry, it is 180. This is pi by 2. This is 370, 3 pi by 2. So at that time, where will be the radiation? Along the antenna axis, it will be 0. So the radiation will be perpendicular, it will be like this. Right? This concept is widely used, so very, very important. Here antenna is located in this direction. I kept antenna here. This is what antenna. So along the direction of antenna, along the antenna axis, the radiation will be 0. The radiation is maximum when it is perpendicular, right? So this concept is very, 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 very important point, right? So, and another thing we have to remember for Hertzian dipole antenna, how many points I have told? I told already 6 points. So these are all the things you must remember. 7th point is the power radiated by Hertzian dipole antenna is I squared R. Okay, right as right. Power radiated is 40 pi square dl by lambda whole square into I naught square. R radiation is 80 pi squared dl by lambda square. Right. Moreover, it is a poor radiator that we know already. Right. Hertzian dipole antenna is a poor radiator. Why it is poor radiator? Hertzian dipole antenna is poor radiator because you see, just I have explained already in the Hertzian dipole antenna. Anyway, I recall it. For dl is equal to lambda by 20, what happens? R radiation will be approximately equal to 2 ohm. So it is very, very small value, and it is not matching with the transmission line, which has a maximum impedance of characteristic impedance of 50 ohm. So impedance matching is not achieved, so maximum power is not transferred. That's why Hertzian dipole antenna is a poor radiator, not used in the real-time scenario, right? So, and another thing is, you see, your power radiated or R radiated is depending not on dl value, it is dl normalized by lambda. So absolute length is not important. What is the length with respect to lambda is important for dipole antenna, Hertzian dipole antenna, because length is, here we don't have an equation dl square, it is dl by lambda. So length is normalized by lambda. So the length with respect to lambda plays crucial role, not absolute length is required, right? So that's all about this session. If you have any doubt, please ask me in comment section. I will clarify. Thank you.